Okay, Bismillahirrahmanirrahim. The topic that we are going to do today is a new topic, and this is other organic chemistry. It's not an extension to any of the topics that you did last year. It's basically a new functional group. Okay, it's called arenes. Right? The learning objective that we are going to cover just today, okay, is the general structural, display, and skeletal formula of arenes or benzene. And then we will describe and explain the shape of and bond angles in benzene molecules in terms of sigma and pi bonds. So this will require you to recall your AS knowledge on sigma and pi bonding, on orbitals, hybridization, that we will look at later on during this lesson. Okay, now there are two major classes of organic hydrocarbons. Okay, so organic compounds are your hydrocarbons, your homologous series, alkenes, alkanes, alcohols, haloalkanes, carboxylic acid, ketones, aldehydes. These are the ones that you have come across in AS. So the ones that we have covered, they're called the aliphatic group. Okay, the aliphatic can be straight or branch chain organic substances, right? They can be ring, like a three-membered ring, a cyclopropane or a cyclobutane, but still they're considered aliphatic. Okay, just because it says straight or branch, the ring falls under aliphatic. Aromatic or arenes is a group that has one or more ring of 6 carbon atoms with delocalized bonding. So I will explain what delocalized bonding means later on. The simplest member of the arene or the aromatic compounds is your benzene. Okay, benzene has the formula C6H6, 6 carbon atom, closed in a ring, connected in a ring of a hexagon, and then there are 6 hydrogen atoms. Okay, so this is actually not the accurate structure of benzene yet. Okay, you may see some textbooks or some in the internet, they will use this structure, but for CIE, they do not want you to draw it like this. Yeah, I'll explain it to you later on. Now, what's inside, how does the structure look like? Basically, this carbon in the ring has an alternative double bond and single bond. Double, single, double, single, double, single. So there are 3 double bonds and 3 single bonds in the carbon ring, inside the carbon ring. Okay, so if we just look at one carbon, this carbon, as you know, carbon has 4 electrons in the outermost shell, therefore it can form 4 bonds. Okay, so if you look at one carbon and the bonds around it, there's one single bond to another carbon, there's a double bond to another carbon, so that's already 3 bonds out of 4 being used. So carbon is only left with 1 bond to form with hydrogen. So that's why at every carbon, there's only 1 hydrogen hanging out. Okay, usually we draw the hydrogen hanging out of the ring. The skeletal formula looks something like this, but again, not quite yet. Okay, we call this the Kekule structure. Kekule is a person. When we draw the skeletal formula, we omit all the carbon and the hydrogen. Okay, but the double bond you have to show, right? So each corner represents carbon. Now, most of the time you'll be drawing the skeletal formula, so you have to remember there is a hydrogen hanging out, even though it's not shown, okay? Per each corner or each carbon will always have 1 hydrogen hanging out that you cannot see, right? The numbering in benzene, it can be clockwise or anti-clockwise. It depends on the smallest numbering system. Okay, later on, I'll explain it to you as we go along. Like, where do you start your numbering? For an aliphatic compound, you can either start from the left or from the right to get your side chain to have a small number, okay, small position, right? For benzene, same thing, right? You can start clockwise. So this is carbon number 1. Oops, sorry. Where is it? Yeah. Okay, so this is carbon number 1, carbon number 2, 3, 4, 5, 6. Okay, so you can either go clockwise or anti-clockwise, right? Before I show you that structure. Right, so in the structure, you can see that the double bond is between carbon 2 and 3, 4 and 5, 6 and 1. Okay, there's another structure we call the resonance structure, or basically it is the same, right? It's the same. If you start your numbering here, 1, ayo, anti-clockwise, 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3. 2 and 3, there's a double bond. 4 and 5, there's a double bond. 6 and 1, there's a double bond. Okay, but later on you will see that the double bond, it doesn't matter. It's not fixed. It's not fixed between carbon 2 and 3, between carbon 4 and 5, and carbon 6 and 1. Okay, so when you see the double bond being drawn like that, fixed, these are all the calculus structure. The actual structure of benzene and what you must always draw at all time looks like this. This one. Okay, this is the most important structure that you will use in all your drawings from now on. Okay, so you have a 6-membered hexagonal ring, 6-corner, okay, hexagonal ring, and then you have a circle inside. That circle tells you the pi bond or the double bond is delocalized. Delocalized means it is not fixed at one position. So actually you can't tell where the double bond is, and that's how the structure or the bonding of a benzene is. The double bond is constantly moving, or we say that the pi electrons are constantly moving in a circle. So you just draw that circle, delocalize, okay? It's not fixed. So I'll talk about that bonding a bit soon after this, okay? Right, so calculase structure. Calculase says that benzene is a hexagonal ring that contains alternative single and double bonds, okay? So whenever you see the double bond, instead of a circle being drawn, that's actually the calculase structure, okay? Why is calculase structure inaccurate? It's not wrong, it's just that not the most accurate, okay? Right, if you look at the structure of calculate, there is a single bond, 3 single bonds, and 3 double bonds, okay? And single and double bonds, they have different bond length, and they are quite distinctive, okay? This is the bond length of a single bond, 0.14 nanometer, and the bond length of a double bond is CC double bond is 0.134 nanometer. Usually, any structure, any organic molecules that have a CC bond will have this particular length, okay, bond length. However, when they did some analytical measurements, when they analyze the structure of benzene, it turns out that the bond length of benzene, okay, all the bond lengths, is 0.139 nanometer. It is not a single bond, nor it is a double bond. It's somewhere in between, okay? The number lies in between. So that means this says calculate structure is not exactly correct. If it contains 3 double bonds and 3 single bonds, then you would see this bond lengths, but you don't see them at all when you analyze it, okay? So that's why we tend to not draw double, single alternatively, okay? The second reason is because if you look at benzene, benzene has 3 double bonds, and double bond is a characteristic of an alkene. An alkene, as you know, goes electrophilic addition reaction from your AS. However, benzene undergoes an electrophilic substitution, okay? So it doesn't work like alkene. So that means this double bond is the special kind of double bond. It's not like the double bond in alkene. And in fact, yes, it is not the same as the double bond in alkene, because this time it is delocalized, it can move, okay? So I'm going to explain to you why the double bond can move. We have to look at the bonding. So this is the structure of benzene that you should be drawing it at all times, okay? You can either draw it as a displayed formula. You draw all your carbon and hydrogen. Your double bond, you will not draw it, you just draw it as a circle, okay? But you know inside this circle, there are 3 double bonds inside here. You just cannot tell the position, where it is. That's why you just draw a circle, okay? Or the easiest one is the skeletal formula, okay? We don't use the term abbreviated formula. Change that to skeletal formula, okay? This one. Change it to skeletal. How do I write text? I cannot move it. Oh, okay. Right, moving on. Sorry. Right, moving on. Now we're going to look at the structure and bonding in benzene, okay? I may have an additional slide here that is not in your notes, but that's okay. The explanation in your notes should be the same. Right, so before we look at the bonding, we need to know the hybridization of carbon atom, okay, in the benzene ring. Now each, okay, I'll talk about that. So there are 6 carbon atoms in a hexagonal ring with 1 hydrogen atom bonded to it, hanging outside of the ring, okay? This is how it looks like, right? Each carbon atom is sp2 hybridized. Okay, how do you know it's sp2 hybridized? Now, what is hybridization? Just to remind you again, when it comes to reaction, only the outermost electron is involved in reaction, okay? And as you know, carbon, it has an electronic configuration of 1s2, 2s2, 2p2. So we are only interested in the outermost shell, which is the second shell. In the second shell, you have an s orbital and 3 p orbitals, px, py, pz, okay? And then here, there's some excitation of electrons happening. So this is how it looks like before hybridization. Hybridization is the mixing of orbitals, okay? And s orbital is spherical. P orbital looks like an hourglass, okay? Right, so when they mix, because it is sp2 hybridized, that means I am mixing my s orbital, which is the only one, and 2 out of 3 of my p orbitals, okay? The 2 stands for 2p orbitals. So mixing 1s and 2p, that means I am mixing these 3, okay? So when I mix these 3 orbitals, I will get out 3 new orbitals as well, okay? So after hybridization, after mixing, I get a new orbitals that are called sp2. Okay, instead of it being separate s and pp orbital, now it becomes sp2 that has a shape like a deflated balloon. Okay, half loop. Now it looks like you have a half loop only. So this is your new orbitals. Okay, and you have 3 of them, and that leaves you with 1 orbital that is unchanged. This is your original p orbital. Okay, your sp2 for each carbon, this is for each carbon. Okay, so if I draw it here, so now I have a purple orbital and a green orbital. Okay, right. So if I draw this orbital on this carbon, if I just focus on here, my sp2 will arrange itself in a planar arrangement. Okay, like that. That's my second sp2 orbital, and this is my third sp2 orbital. Okay, and then I'm losing my cursor. Okay, so sp2 orbitals are the one that will be involved in a sigma bond. A sigma bond, the easiest way to identify a sigma bond is a single bond. Okay, so my purple orbitals or my sp2 orbitals will be involved in sigma bond. So carbon with hydrogen is a sigma bonding or sigma overlap. So the sp2 of the carbon atom overlaps with the s orbital of the hydrogen, which is not, you cannot see it here, so I'm just going to draw. S orbital is a, oops, is a, just a circle, a sphere. Okay, so that's s orbital of hydrogen, maroon, and the sp2 of my carbon atom, one of them. So that is a sigma overlap. Okay, this carbon will also form a sigma overlap with the other carbon. Remember, each of this carbon will have an sp2 around it. So I'm going to use pink just to show you that this other carbon also have an sp2 orbital, also arranged flat, planar. Okay, so this is an sp2 of this first carbon, and the pink one is also showing you the sp2 orbitals of the second carbon. Okay, right. Let me just number them first. This is first carbon, and this is second carbon. Okay, right. So the sigma bonding that I was talking about just now is between carbon and hydrogen, sp2 of carbon and s orbital of hydrogen. The second sigma bond is the sp2 of carbon 1 and the sp2 of carbon 2. That's the sigma bond. Okay. The third sigma bond is, I need to draw another 1, 2, 3, 4, 5. This is carbon 6. Carbon 6 will also have the same system. I'm running out of colors. I'm going to use red. Okay, so sp2 of this carbon number 6, sp2, sp2. Okay, so back to carbon number 1. First sigma bond, second sigma bond. The third sigma bond is the sp2 of carbon 1 and the sp2 of carbon 6. Okay, I hope you can see that. Now, so there are 3 sigma bonds per carbon atom. I'm only looking at carbon number 1. Okay, first sigma bond, second sigma bond, and the third sigma bond. That leaves me with 1 more bond because carbon needs to have 4 bonds. Okay, that fourth bond is not a sigma bond. If you look at the orbitals that I have here, I've already used the 3 of my sp2 orbitals. I'm left with the p orbital that is unchanged. Okay, so I will use green. So that means there is a p orbital that looks like this. This p orbital is perpendicular to your sp2 orbitals. If sp2 is flat, horizontal, then your p orbital will be vertical. Okay, so each carbon again will have a p orbital that looks like this. Oops. Okay, just gonna draw it. right? And in this p orbital, there is 1 electron per carbon. Okay, and this electron in the p orbital is the one involved in the formation of a pi bonding. Okay, if you remember, a double bond consists of a C double bond C consists of 1 sigma and 1 pi. Okay, so going back to the pi bond, right? So a pi bond is an overlap between one p orbital of one carbon, carbon 1, and the p orbital of carbon 2. Okay, so you can imagine there's an electron here and there's another electron here from the other carbon, and you just need 2 electrons to form 1 pi bond. Okay, since there are 6 electrons, 1, 2, 3, 4, 5, 6 electrons, 6 p orbitals, they form 3 pi bonds. Okay, and as you know that there are 3 double bonds. Now, because of the way that your p orbital is arranged, okay, they are arranged like that, this means that the electrons can move in a ring. They can move like this. What's happening here? Sorry. Okay. So these electrons, the green electrons, are actually not fixed. They move around like that. That's why you see the circle. Okay. Don't forget the bottom part is also an area where your electrons, and orbital is the region where your electrons can be found. So they can also move at the bottom, and there's also a bottom ring like that. Okay, maybe not easy to see, right? So that's why we say that there is a delocalization. So that delocalization is only your pi system. Your sigma system is happy with their single bond. It's only the double bond, the pi bond, that can move from one place to another because they are all aligned. The p orbital are all aligned nicely, so they can provide. They are a system that can allow the electrons in the pi bond to move around, not fixed. Okay. Okay, let's look at the explanation. I hope you can understand. Each carbon atom is bonded to 2 other carbon atoms and 1 hydrogen atoms by sigma bonds. So if you look at this diagram that already looks complicated, is the purple, pink, and red orbitals overlapping. These are all your sigma bonds. Okay, carbon 1, carbon 2, carbon 1, carbon 6, carbon and hydrogen. These are all sigma bonds. Okay, leaving 1 unused electron in a p orbital. So the green orbital is your p orbital, and there is 1 electron. It lies perpendicular. It lies perpendicular to the plane of the ring. Okay, and the 6 p electrons are delocalized. So if I draw 6 p orbitals, okay, they are delocalized. Okay, moving on. Okay, I'm gonna clear my drawing now. So this is basically saying the same thing. Each carbon atom is sp2 hybridized. This leaves 1 electron spare in the p orbital. Since there are 6 carbon atoms, each carbon atom contributes 1 electron to form pi bond. Okay, 6 electrons in the p orbital produces 3 pi bond. Okay, because to form 1 bond, you need 2 electrons. So instead of having 3 localized double bonds or 3 localized pi bonds, the double bonds are delocalized. Okay, delocalized means not attached to a particular atom or not fixed at one position. You don't know if it's between position carbon 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6. It can 6 and 1. It can be anywhere. Okay. You know that the p orbital lies perpendicular to the plane. So there is a region above and below the plane of a benzene molecule, okay? So when they ask you to draw the electron density of the pi orbital in a benzene ring, you will draw like a donut above and below the plane. This represents your p orbitals because your p orbital contains two lobes that are above and below. That's why you see this two donut ring to show the delocalized system. Okay, so here are the features of bonding. So that's the one that I explained to you before. This is the bonding in a benzene ring. Now, just to summarize the features of a benzene ring, the bonding and its structure. We know that the reason why we reject calculus structure is because the carbon-carbon bonds inside your benzene ring all have the same length, which was 0.139 nanometer, okay? It's not a single, it's not a double, it's an intermediate, okay? And they all have the same bond length. Carbon 1, carbon 2, carbon 2, carbon 3, 3 and 4, 4 and 5, 5 and 6, 6 and 1. Now, so each carbon atom, as you can see, to know the shape, you need to look at one central atom and to count the number of electron density or electron region, or what we say the bonds around it. So this carbon atom, if I just choose one, there are 1, 2, 3 bonds around it. Okay, so when you have 3 bonds around a central atom, it has a shape of trigonal planar. So carbon number 1 is trigonal planar, carbon number 2 is a trigonal planar. Same goes for 3, 4, 5, and 6. They all have, each of this carbon atom only have 3 bondings around it. So because they are all trigonal planar, this makes your benzene molecule a planar molecule, okay, a flat molecule. Each carbon atom is sp2 hybridized, so you just have to memorize that, okay? Each carbon atom has 3 sigma bonds, 3 single bonds, 1, 2, 3, okay? So that one you already know. And each carbon atom has 1 unhybridized p orbital that lies perpendicular, okay? This p orbital, the electrons in the p orbital is the one that forms your delocalized pi bond. Okay, so this is how it looks like. Now, again, this drawing is not that accurate because I'm saying that the pi bond or the pi electron is fixed here, but actually they can move. Okay, since there are 6 p electrons or pi electrons, that means you form 3 bonds. But again, I repeat, this drawing is not accurate because I'm saying that the pi bond is fixed when actually the pi bond can move. But even though they move, there will always be only 3 pi bonds when you freeze it, when you freeze the time. Okay, there will not be 6 pi bonds, only 3 pi bonds. The delocalized ring of electrons lie above and below the plane. So if they ask you to show the delocalized system of the pi electrons, you show like a donut ring above and below the plane. Okay, so that is all for that I want to cover today, which is the structure and bonding of benzene. I know it was long, but because it requires you the knowledge of the section that you don't really like in chemistry, which is overlap, sigma pi, hybridization. Yeah, so do you need to know that? Yes, because they can ask you what type of overlap is between carbon and carbon, or what type of overlap is between carbon and hydrogen. And then they will ask you about sp2 hybridization. Will they ask you to draw it? No. Okay, well, so far, no. So hopefully they will not ask you in November. Okay, right, that is all. Is there any questions before we go?